So now let's talk about graph-based segmentation. So in graph-based segmentation, images are considered as graphs, okay? And basically each node, we can represent for, let's say, for every pixel, and the edges, basically the connections between the pair of pixels, okay, they are weighted by the similarity of the two pixels. Okay, so this is just a representation based on a graph. So for example, we have the weighted the weighted connections. As we can see here in this graph, we have A, B, C, D, and E, and these represent, for example, particular pixels. Okay, and they have different weights depending on the similarity. So if they have a high similarity, they have a high weight. For example, they have 7. If they have very low similarity, they have, let's say, weight of 1. So we can actually represent this also as a weight of matrix, as we can see here, depending on the connections from each point to another point. For example, we have from from A, basically from A to A, there's 0, right? But from A to B, we have 1. From A to C, we have 3. To D, we cannot actually connect, so we specify this as infinity, and it's the same for E. So we just reconstruct this weight matrix. So now, the cutoff graph, basically this is the actual algorithm that we're gonna perform. How do we cut the different groups of pixels, right? So a cut of the graph is basically the set of connections. Okay, is that such as the removal of this particular connection disconnects two actual sets of elements. Okay, so for example, this is one particular cut, or it can be this cut, or it can be this cut. Okay, so what we're gonna do is that the cut will be based on the minimum weights. Okay, so as I mentioned before, we have different weights, so we're gonna perform the cut on the sum of the different weights. So for example, here we have a particular graph on the left, and as we can see, there are basically different nodes connected with different lines that represent particular weights, and we perform in this case the cut based on the minimum, which is the one that have 0.1. Okay, so once we perform this particular cut, now we end up with two clusters that have a different number of nodes and different connections. So this is basically the principle of minimum cut and clustering based approach. So again, if we have an image in which we have a representation of different elements as pixels, let's suppose that this image consists of a region of a center with a particular color, and we have another region which is the surrounding with a different color, and then so we classify this as the connections. So the ones that have a different color, basically they have a minimum weight, and we can just perform the cut in that space, and then be able to segment out this portion. So this is basically the overview of spectral clustering. As we can see here, we can compute similarities based on the different minimum weights, or we can just basically cut everything and then be able to detect particular blocks of images. These are some of the examples of cut-based segmentation. As you can see here, we have a better, a more clear segmentation, which is actually quite good. Okay. However, this minimum cut is not always the best solution. Sometimes we have the same weights in different portions of the image, and sometimes they are not exactly the best cut to perform. So how can we fix this? Well, one way is to normalize the cut. That is that we actually penalize large segments by, in this case, we normalize the size of the segments. So we need to actually cut only when we have a larger larger cluster that needs to be separated. Okay, so the actual way to normalize is basically by computing a particular equation that you can see here in the screen, and basically here we basically normalize by computing the volume. The volume in this case is just the sum of the sum of the cost for all the connections that touch a particular point. Okay, so this is basically how we actually normalized. This is just another example of the resulting image after we normalize. So let's go ahead and then talk about structure of motion. So structure of motion basically is a very interesting problem, in which, given many images, so the problem is how can we figure out where all these images were taken from, and how we can actually use the information contained in these images to build a 3D model of the scene or the object that we just took a picture. So for example, this is an example of what we are capable of to do. Basically, we have many images, and then we can reconstruct all these images into a 3D space representation. So this is basically the structure of motion problem. So initially we have several input images, okay, with many points. Okay, so we have many points that they actually have some correspondences among all these different images. So the output should be basically the structure, which is the 3D location of each point, and also we can come up with the camera parameters based on the rotation and translation for the particular picture that was taken. So the objective basically is we can just minimize the projection error. So we need to actually come up with the best solution to find to fix these points of correspondences. So this is one particular example of how we can actually compute, how we can actually reconstruct a particular object from many images. So let's see how this is performed. Okay, so up to now we have seen different concepts. For example, we have seen 2D transformations between different images. In the last lectures, we already talked about translation, affine transformations and homographies, right? We also notice that it's necessary to know the fundamental matrices, because they still represent the relationships between these 2D images. So in this case, for this particular topic of motion structure, the new concept is just how we can explicitly represent the 3D geometry of the cameras and points. So it's just basically how we can actually reconstruct the different parameters. Okay, so for example, if we have a particular image, there are some steps that we need to follow. First, we need feature detection. Okay, so we need to find what features are good to be able to reconstruct the image. So once we have these particular features, then we need to match the features of the different images that correspond to each other. Okay, so basically 2 steps: feature detection and then feature mapping. So for feature detection, there are some features that are very famous. They are called SIFT features, which stands for Scale Invariant Feature Transform. So these images, basically, they have particular features that can be detected based on the texture of the image. So these features we can basically compare to these other images, and we can find the correspondences to these other images. We can find if these features are the same in different images. So once we have this, we need to refine the matching, because sometimes those features, they made the mistakes and they match to other features that do not correspond to each other, and this is a problem that needs to be fixed, and by refining this feature matching based on a different algorithm that is called ransack algorithm. So this ransack is used to estimate, the fundamental matrix between each pair of features. So let me explain how this is done. So suppose we have these two images. They actually are this, they contain part of the same scene. So from these images, okay, we can match two particular points. Okay. So here, let's say we are matching different points, and then some of them, they actually correspond to the actual point that they should correspond to. But sometimes we have some errors. These are marked with the red arrows, and these errors are quite sometimes difficult to find. But the way to find is by using the following approach. So in this case, the problem is, how do we find the bad matches, right? So here, what we do is we select one particular match, okay, based on two features, okay, and then we count the inliners. The inliners are basically the ones that are similar to this particular match. So in this case, we count and we see that in this case we have 4 inliners, okay, and then we count the outliners, which are only 2 of them, right? So we do this process for all of them, for all the different matches, and then we come up, for example, for the different outline, for the match of the outliners. So we count, the ones that are similar to that one, and we see that there's only a few of them. So we can know the difference of numbers between the inliners and the outliners, and this is the way we can actually find what are the features that are not correct. So as an overview of this ransack algorithm, okay, we perform a loop first by selecting 4 feature pairs, okay, as random, and then we compute the homography of H, which is basically the actual direction of correspondences, and then we compute the inliners. Basically, we count the number of inliners, the number of other matches that are similar to this one, and then again we perform this as a loop, okay, and we keep, at the end, we keep the largest set of inliners, and the other ones, they just remove, they correspond to the bad outliners. And finally, we recompute the least squares of this homography by estimate of all the inliners. So the question is, now how can we do with this? We already have the match of this all these points, right, or these features. So if we have now many images taken, let's say, from the same camera with the different positions, we can see that we have different features, okay, that they correspond to each other, and we can also try to find the parameters in the sense of rotation and translation for each camera position. How do we do this? Well, we can actually perform the matching based on a particular point, okay. As we can see here, we can match a particular point in 3 different images, and then we can come up with the different angles, and then we can find the actual rotation and translation. So this is just a problem of minimization, in which we are using the rotation, translation, and position matrix of a particular point. So now this this minimization is called the minimize. We basically minimize the sum of square projection of errors by basically finding the observed image location, okay, and then we have a predicted image location based on the rotation and translation, and then we have the indicator variable, which is a point that is visible in a particular image. So by using this minimization equation, okay, basically we optimize based on a procedure called nonlinear least squares. Okay, we're not gonna go into the actual details of all the mathematics that go through this, because we're trying to learn the actual concepts of what is happening, what is going on, and then we want to actually apply it into real applications. Now, this structure of motion, is it always unique and solvable? Well, the answer is no, because as you can see here, we can have very similar features that sometimes they can be confused if we change into different position or orientation from the camera. They can be confused. However, in the cases where we succeed, we have many examples of actual 3D reconstruction based on this approach. Some of the applications are 3D modeling. Also, as we mentioned before, we also have 3D robot navigation and map making, in which an autonomous robot can just wander around the room and start taking pictures and then try to build a particular map. So now let's talk about motion analysis.